Hello there, and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if gravity itself has softened. Because tonight, we're going to explore something truly amazing. We're going to imagine what it would be like to sleep inside a quiet supernova. Now, you might be thinking, supernovas are explosions. They're violent, they're bright. How could they be quiet? After the explosion, after the light fades, something beautiful remains. A supernova remnant. A vast cloud of gas and dust expanding slowly through space. It's quiet. It's peaceful. It's one of the most beautiful things in the universe. You'll hear about stars that explode with the power of billions of suns. You'll learn about the elements they create, the same elements that make up your body. You'll discover what happens after the explosion, when the light fades and the remnant drifts through space. And you'll imagine what it would be like to float inside one of these cosmic clouds, surrounded by the remains of a star that died long ago. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. Chapter 1. What is a supernova? The death of a star. A supernova is one of the most powerful events in the universe. It's the death of a star, but it's also a beginning. When a massive star explodes, it creates new elements. It scatters them across space, and it leaves behind something beautiful, a supernova remnant, a quiet cloud of gas and dust that drifts through the galaxy for thousands of years. Stars are born from clouds of gas and dust. They shine for millions or billions of years, and then they die. Most stars die quietly, they fade away slowly, but the biggest stars die with a bang. They explode, they become supernovas, and in that explosion, they create the elements that make up everything around us. The iron in your blood, the oxygen you breathe, the calcium in your bones. All of it came from stars that exploded long ago. A supernova happens when a massive star runs out of fuel. Stars shine by fusing hydrogen into helium. This process releases energy. It's what makes stars hot and bright. But eventually, the hydrogen runs out. The star starts fusing heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes silicon. And silicon becomes iron. But iron is special. Iron can't be fused to release energy. When a star's core becomes iron, fusion stops. And without fusion, the star collapses. The collapse happens in seconds. The core, which was the size of Earth, shrinks to the size of a city. The temperature rises to billions of degrees. The pressure becomes enormous. And then the outer layers of the star fall inward. They hit the collapsed core, and they bounce back. This creates a shock wave, a wave of energy that travels outward at incredible speed. This is the supernova explosion. Scientists have studied this process using computer simulations. They've found that the collapse is incredibly fast. The core shrinks from the size of Earth to the size of a city in less than a second. In that moment, the temperature jumps to over 100 billion degrees. That's hotter than anything else in the universe. Hotter than the Big Bang itself. The pressure becomes so intense that atoms are crushed. Electrons are forced into protons, creating neutrons. The core becomes a neutron star, an object so dense that a teaspoon would weigh billions of tons. All of this happens in less than a second. It's one of the fastest events in the universe. But from that moment of collapse comes the explosion, the shock wave, the light, the quiet supernova that follows. The explosion is incredibly bright. For a few weeks, a single supernova can outshine an entire galaxy. It releases more energy in those few weeks than our sun will release in its entire lifetime. The light travels across space. It reaches Earth, and we see it as a new star in the sky. A star that wasn't there before. A star that will fade away in weeks or months. But the explosion itself is just the beginning. After the light fades, something remains. A supernova remnant. A cloud of gas and dust that expands slowly through space. This is the quiet supernova, the peaceful aftermath of a cosmic explosion. Supernovas are rare. In our galaxy, the Milky Way, a supernova happens about once every 50 years. But there are billions of galaxies, so somewhere in the universe a supernova is happening right now. As you rest, a star is exploding somewhere far away. Its light is traveling through space, and in thousands or millions of years, it might reach Earth. We might see it, a new star in the sky, a reminder that the universe is always changing. Interestingly, the last supernova we saw in our galaxy was in 1604. That's over 400 years ago. Astronomers call it Kepler's supernova, named after the famous astronomer who studied it. So why haven't we seen one since? It's not that they're not happening. It's that dust in our galaxy blocks our view. We can't see through all that dust. But astronomers think there have been several supernovas since then. We just couldn't see them. They're hidden behind cosmic clouds, but we can detect them in other ways. X-rays, radio waves, these can pass through the dust, so we know they're happening, even if we can't see them with our eyes. Kepler's supernova was special. It was visible for over a year. Kepler himself watched it. He wrote about it. He measured its position. He tried to understand what it was. At the time, people thought it might be a new star, or a comet, or something else entirely. They didn't understand supernovas yet, but Kepler's observations helped. They gave us a record, a historical record, of a supernova that happened over 400 years ago. Today, we can still see its remnant. It's about 20,000 light years away. It's still expanding, still glowing, still beautiful. The quiet supernova from 1604, still with us today. Before Kepler's supernova, there was Tycho's supernova in 1572. Tycho Brahe was a famous astronomer. He saw a new star appear. He studied it carefully. He measured its brightness. He watched it fade. His observations were detailed, very detailed. They helped scientists understand that stars could change, that new stars could appear, that the sky wasn't fixed. Today we can see Tycho's remnant too. It's about 8,000 light years away. It's still expanding, still beautiful. The quiet supernova from 1572, still expanding, still peaceful. Scientists have found that there have probably been about 20 supernovas in our galaxy since Tycho's, but we only saw 2 of them. The others were hidden, behind dust, too far away, or too dim, but we can find their remnants using X-ray telescopes, radio telescopes, infrared telescopes. We can see them, even if we didn't see the explosion. The quiet supernovas, hidden, but still there, still beautiful. There are 2 main types of supernovas. Type 1 happens when a white dwarf star explodes. A white dwarf is what's left when a small star dies. It's dense, it's hot, but it's not massive enough to explode on its own, unless it has a companion. If a white dwarf orbits another star, it can steal material from its companion. When it gains enough mass, it explodes. This is a type Ia supernova. These explosions are all about the same brightness. Astronomers use them to measure distances across the universe. Type 2 supernovas happen when a massive star explodes. These are stars that are at least 8 times more massive than our Sun. They live fast and die young. A star 10 times more massive than our Sun might live for only 10 million years. That's short compared to our Sun, which will live for 10 billion years. But these massive stars burn bright. They use up their fuel quickly, and when they run out, they explode. The explosion creates new elements. During the explosion, the temperature and pressure are so high that elements heavier than iron can form: gold, silver, platinum, uranium. All the heavy elements in the universe were created in supernova explosions. Without supernovas, these elements wouldn't exist. And without these elements, life as we know it wouldn't exist. You are made of star stuff, literally. Every atom in your body was created in a star. Some were created in supernovas. Some were created in other stellar processes. But all of them came from stars. Scientists have actually measured this. They've studied the elements in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe. They've traced these elements back to their origins. Most of the iron came from supernovas. Most of the oxygen came from massive stars. Even the gold in jewelry came from supernova explosions. Astronomers estimate that about 93% of all the atoms in your body came from stars. The rest is mostly hydrogen, the simplest element, the one that was created in the Big Bang. So you're mostly star stuff, with a little bit of the universe's first atoms mixed in. But here's something even more amazing. Scientists have found that different parts of your body have different origins. The iron in your blood, that came from type 2 supernovas, the kind that happen when massive stars explode. The calcium in your bones, that came from both supernovas and smaller stellar explosions. The carbon that makes up most of your body, that came from stars that were smaller, stars that didn't explode, but still created elements, still scattered them into space. Even more interesting, researchers have discovered that the elements in your body aren't all the same age. Some atoms are older than others. The hydrogen, that's ancient, from the Big Bang, almost 14 billion years old. The iron, that's younger, maybe only a few billion years old, created in a supernova that happened before our solar system formed. The gold, that might be even younger, created in a neutron star collision, a rare event, but it happened. And now that gold might be in a ring, or a necklace, or even in tiny amounts in your body. It's all connected, all part of the cosmic cycle, all part of the quiet supernova. When a supernova explodes, it sends material flying outward at incredible speeds. The material travels at thousands of kilometers per second. It expands into space. It mixes with the interstellar medium, the gas and dust that floats between stars. Over time, the material cools. It slows down, but it keeps expanding. For thousands of years, it drifts through space. This is the supernova remnant, the quiet supernova, the peaceful cloud that remains after the explosion. Supernova remnants are beautiful. They glow with different colors: red from hydrogen, green from oxygen, blue from other elements. They form intricate shapes. Some look like bubbles, some look like rings, some look like clouds. They're some of the most photographed objects in the night sky: the Crab Nebula, the Veil Nebula, the Vela supernova remnant. These are all supernova remnants. They're all quiet now, but they were once violent explosions. They were once stars that died. The Crab Nebula is one of the most famous supernova remnants. It's about 6,500 light years away. A light year is the distance light travels in 1 year, about 9.5 trillion kilometers. So the Crab Nebula is very far away, but we can still see it with a telescope. It glows with beautiful colors: red, green, blue. It's expanding at about 1,500 kilometers per second. That's fast. But from our distance, it looks like it's moving slowly. The expansion has been going on for almost 1,000 years, and it will continue for thousands more. The supernova that created the Crab Nebula was seen on Earth in the year 1054. Chinese astronomers recorded it. They called it a guest star. It was visible during the day for 23 days, at night for almost 2 years. Then it faded away, but the remnant remained, the cloud of gas and dust, the quiet supernova. It's still there today, still expanding, still glowing, still beautiful. Chinese astronomers weren't the only ones watching. Japanese and Arabic astronomers also wrote about this supernova. They all saw the same bright star appear where no star had been before. The Chinese records are the most detailed though. They tell us exactly when it appeared: July 4th, 1054. They describe it as being as bright as Venus, maybe even brighter. It was so bright that you could see it during the day. That's rare, very rare. Most supernovas are only visible at night, but this one was special. It was close enough and bright enough to shine even when the sun was up. Interestingly, there's no record of this supernova from European astronomers. Why? We're not sure. Maybe the weather was bad. Maybe they weren't looking. Or maybe the records were lost. It's a mystery, but we know it happened because the remnant is still there. The Crab Nebula proves it. The quiet supernova that started almost 1,000 years ago is still expanding today. Scientists have studied the Crab Nebula for decades. They've measured its expansion carefully. They found that it's actually expanding faster than expected. The pulsar at its center is adding energy. It's like a cosmic engine, keeping the remnant bright, keeping it active. Astronomers discovered that the pulsar is slowing down, very slowly, about 1 second every 30 years. This tells us how much energy it's losing, how much it's giving to the remnant. It's a beautiful connection between the dead star's core and its expanding cloud. Using the Hubble Space Telescope, astronomers have measured the expansion rate precisely. They found that the nebula is growing by about 1,500 kilometers per second. That's fast. But here's something interesting. The expansion isn't uniform. Some parts are moving faster than others. The fastest parts are moving outward at about 2,100 kilometers per second. The slowest parts are moving at about 1,200 kilometers per second. This tells us that the explosion wasn't perfectly spherical. It was a bit lopsided, like a balloon that's not quite round, but still beautiful, still expanding, still the quiet supernova. Scientists have also measured the mass of the Crab Nebula. They found that it contains about 4.6 times the mass of our Sun. That's a lot of material. All of it was once inside a star that exploded almost 1,000 years ago. Now it's spread across 11 light years of space. That's huge, but the material is so thin, so spread out. That's what makes it peaceful. The quiet supernova. Supernova remnants are important for the galaxy. They enrich the interstellar medium with heavy elements. They create shockwaves that compress gas clouds. These compressed clouds can collapse and form new stars. So supernovas don't just destroy, they also create. They're part of the cycle of star birth and death. Stars are born, they live, they die, they explode, and their remains help create new stars. It's a cycle that has been going on for billions of years, and it will continue for billions more. The material in a supernova remnant is very thin, much thinner than Earth's atmosphere. In fact, it's much thinner than the best vacuum we can create on Earth. But it's not empty. It contains gas and dust, mostly hydrogen and helium. but also heavier elements, carbon, oxygen, iron, and more. These elements were created in the star before it exploded, and they were scattered by the explosion. Now they drift through space, they mix with other material, and eventually they might become part of a new star, or a new planet, or even a new form of life. The temperature in a supernova remnant varies. Near the center, where the explosion happened, it can be millions of degrees. But as you move outward, it gets cooler. At the edges, it might be only a few thousand degrees, still hot by human standards, but cool compared to the center. The material is also moving, expanding outward, but slowly. After thousands of years, the expansion has slowed down. The material is drifting, floating, peaceful. If you could float inside a supernova remnant, what would you see? You'd see glowing gas, red, green, blue. You'd see dust particles, tiny grains of carbon and silicon. You'd see the remains of a star, but you wouldn't see much else. The material is so thin that you could see through it. You could see the stars beyond, the galaxy beyond. You'd be floating in a cloud, a beautiful, colorful cloud, but a cloud that's mostly empty space. The colors come from different elements. Hydrogen glows red, oxygen glows green and blue, sulfur glows red, nitrogen glows red. These elements are excited by the energy from the explosion. They absorb energy, and they release it as light. Different elements release different colors, so the colors tell us what the remnant is made of. They tell us the story of the star that died. Supernova remnants also emit other types of radiation, X-rays, radio waves. These are invisible to our eyes, but we can detect them with special telescopes. X-ray telescopes show us the hot gas, the material that's still very hot from the explosion. Radio telescopes show us the structure, the shape of the remnant, how it's expanding, how it's interacting with the surrounding material. Some supernova remnants have pulsars at their centers. A pulsar is what's left of the star's core. It's a neutron star, an object so dense that a teaspoon of it would weigh billions of tons on Earth. It's spinning, and it's emitting beams of radiation, like a cosmic lighthouse. The beams sweep across space, and when they point toward Earth, we see a pulse, a flash of light or radio waves. That's why they're called pulsars, pulsating stars. The Crab Nebula has a pulsar at its center. It spins 30 times per second. That's fast, very fast. The beams of radiation sweep across space, and we see pulses, 30 pulses per second, a steady rhythm, a cosmic heartbeat. The pulsar is the remains of the star's core, the part that didn't explode, the part that collapsed into a neutron star. It's still there, still spinning, still pulsing. A reminder of the star that once was. Remarkably, scientists have actually detected this pulsar's pulses in visible light. Most pulsars only pulse in radio waves, but the Crab pulsar is so powerful that you can see it pulse with your eyes. If you had a telescope powerful enough, it flashes on and off, 30 times per second. Too fast for your eyes to see, but if you could slow it down, you'd see it. A tiny star, flashing, like a cosmic lighthouse. Astronomers discovered this in 1969. It was one of the first times scientists saw a pulsar in visible light. It proved that these spinning neutron stars are incredibly powerful. Even after almost 1,000 years, still pulsing, still shining, still beautiful. Supernova remnants don't last forever. Over time they expand, they cool, they mix with the interstellar medium, they fade away. After about 100,000 years, a supernova remnant is no longer visible. It has expanded so much that it's too thin to see. It has mixed with the surrounding material. It has become part of the interstellar medium, but the elements remain. The heavy elements that were created in the explosion, they're still there, still drifting through space, still waiting to become part of something new. So a supernova is both an end and a beginning. It's the death of a star, but it's also the birth of new elements, the creation of material that will become new stars, new planets, new life. It's violent, but it's also beautiful. It's bright, but it also creates something quiet. A supernova remnant, a peaceful cloud that drifts through space. The quiet supernova, the beautiful aftermath of a cosmic explosion. Chapter 2. The explosion and its aftermath, from violence to peace. When a massive star explodes, the explosion happens in stages. First, the core collapses. Then the outer layers fall inward. They hit the collapsed core, and they bounce back. This creates a shock wave, a wave of energy that travels outward. It takes about a day for this wave to reach the star's surface. When it does, the star brightens dramatically. It becomes visible across the galaxy, or even across the universe. The brightness peaks after about 20 days. During this time, a supernova can outshine an entire galaxy. It releases as much energy in a few weeks as our sun will release in 10 billion years. That's a lot of energy, an incredible amount, but most of it is in the form of light, visible light, the light we can see, but also invisible light, ultraviolet, X-rays, gamma rays, all traveling outward at the speed of light. Scientists have measured this energy carefully. They found that 99% of a supernova's energy actually comes out as neutrinos. Those ghostly particles that barely interact with anything. Only 1% becomes light. But that 1% is still enormous. It's enough to outshine galaxies. It's enough to be seen from billions of light years away. The rest of the energy? It's carried away by those invisible neutrinos. Billions and billions of them, streaming through space, through everything, even through you, right now. Neutrinos from ancient supernovas are passing through your body, millions of them every second. You can't feel them, you can't see them, but they're there, a reminder of the universe's power. To put this in perspective, scientists have calculated that during a supernova explosion, about 10 to the 58th power neutrinos are released. That's a 1 followed by 58 zeros, an unimaginable number. Most of these neutrinos pass right through everything. Through the star, through space, through Earth, through you, without stopping, without interacting. They're like ghosts, invisible, silent, but carrying most of the energy from the explosion. Interestingly, while most neutrinos pass through without a trace, a tiny fraction do interact. Scientists have built huge detectors deep underground to catch these rare interactions. These detectors are filled with water or other materials. When a neutrino does interact, it creates a tiny flash of light. Scientists can detect this light. It's incredibly difficult, but it works. We've detected neutrinos from supernovas, from the death of stars. It's amazing that we can detect something so ghostly, so invisible, but so important. The quiet messengers of stellar death. The light from a supernova can be seen from billions of light years away. The farthest supernova ever seen was about 10 billion light years away. That means the light we see left the star 10 billion years ago, when the universe was young. We're seeing the death of a star that happened long before Earth even existed. The light has been traveling through space for billions of years, and is just now reaching us. After the brightness peaks, it starts to fade. The light dims, but it doesn't disappear immediately. It takes weeks or months for the light to fade completely. During this time, the supernova is still visible, but it's getting dimmer, day by day, week by week, until finally it's gone. The star that was there is no longer visible, but something remains. The supernova remnant, the cloud of gas and dust that was ejected by the explosion. The material ejected by a supernova travels at different speeds. The fastest material moves at about 10,000 kilometers per second. That's about 3% of the speed of light. Very fast. But most material moves slower, about 1,000 to 5,000 kilometers per second. Still fast, but not as fast. The material expands outward. It forms a shell, a bubble of gas and dust. This is the supernova remnant. As the remnant expands, it interacts with the surrounding material, the interstellar medium, the gas and dust that floats between stars. The remnant pushes this material aside. It creates a shock wave, a wave of compressed gas. This shock wave can trigger star formation. It compresses gas clouds, and compressed gas clouds can collapse to form new stars. So supernovas don't just destroy, they also create. They're part of the cycle of star birth and death. The shockwave also heats the material, both the material from the supernova and the material it's pushing into. The temperature can reach millions of degrees, hot enough to emit X-rays. That's why supernova remnants glow in X-rays. The hot gas is emitting high-energy radiation that we can't see with our eyes, but we can detect it with X-ray telescopes. Over time, the remnant expands, it gets bigger, but it also gets thinner. The material spreads out, the density decreases. After 1,000 years, a typical supernova remnant is about 10 light-years across. That's huge. Our solar system is only about 0.1 light-years across, so a supernova remnant is 10,000 times larger than our solar system. But the material is very thin, much thinner than Earth's atmosphere. Scientists have measured the expansion of many supernova remnants. They've found that the expansion follows a pattern. At first it's very fast, thousands of kilometers per second, but it slows down over time. After 1,000 years, it might be moving at only a few hundred kilometers per second. Still fast, but much slower than at the start. This slowing happens because the remnant is pushing against the interstellar medium, the gas and dust between stars. It's like pushing through water. There's resistance. The expansion slows, but it never stops completely. The remnant keeps expanding for thousands of years until it becomes too thin to see, but the expansion continues, even after it's invisible. The quiet supernova keeps moving, forever. After 10,000 years, the remnant might be 50 light-years across, even bigger, but even thinner. The expansion is slowing down. The material is mixing with the interstellar medium. It's becoming part of the galaxy, but it's still there, still expanding, still glowing, still beautiful. The quiet supernova, the peaceful aftermath of a violent explosion. The shape of a supernova remnant depends on several things. The shape of the explosion, the density of the surrounding material, the magnetic fields in the area. Some remnants are spherical, perfect bubbles. Others are irregular, twisted, distorted. Some have filaments, long, thin structures that look like threads. These filaments are where the material is denser, where it glows brighter. The Veil Nebula is a beautiful example of a supernova remnant. It's in the constellation Cygnus, the Swan. It's about 2,100 light-years away. The supernova that created it exploded about 8,000 years ago. The remnant has expanded to about 110 light-years across. It glows with beautiful colors, red from hydrogen, green and blue from oxygen. It looks like a veil, a thin, delicate veil floating in space. Astronomers have studied the Veil Nebula with many different telescopes. The Hubble Space Telescope has taken stunning pictures of it, showing details we never saw before. The filaments are incredibly thin. Some are only a few light-years thick, but they stretch for dozens of light-years. like cosmic threads, beautiful threads. The colors are caused by different elements glowing. But here's something interesting. The colors also tell us about the temperature. Red regions are cooler, about 10,000 degrees. Green and blue regions are hotter, up to 50,000 degrees. That's still hot, but much cooler than the millions of degrees at the center. The quiet supernova has cooled down, but it's still glowing, still beautiful. Scientists have also discovered that the Veil Nebula is actually made of three main parts: the Eastern Veil, the Western Veil, and Pickering's Triangle. Each part is expanding at a slightly different speed. The fastest part is moving at about 600 kilometers per second. That's been slowing down for 8,000 years, but it's still moving, still expanding, still part of the quiet supernova. Astronomers have studied the Veil Nebula in detail. They found that it's actually made up of several different parts, like pieces of a broken shell. Each piece is expanding at a slightly different speed. The fastest parts are moving at about 600 kilometers per second. That's fast, but it's been slowing down for 8,000 years. Scientists have also discovered that the Veil Nebula is interacting with other clouds of gas. It's pushing into them, creating new structures, new patterns. It's not just drifting, it's actively shaping its surroundings. Even after all these years, the quiet supernova is still at work. The Veil Nebula has filaments, long, thin structures that glow brightly. These filaments are where the material is compressed, where the shockwave has passed. They're beautiful, delicate, like threads of light. They show us the structure of the remnant, how it's expanding, how it's interacting with the surrounding material. Supernova remnants also contain dust, tiny grains of carbon and silicon. These grains were formed in the star before it exploded, or they were formed in the explosion itself. The dust is mixed with the gas. It's part of the remnant, and it's important. Dust grains can help form new stars. They provide surfaces where molecules can form. They help cool the gas. They're tiny, but they're important. The dust in supernova remnants is very small, typically about 0.1 micrometers across. That's about 1,000 times smaller than a grain of sand, but there's a lot of it. A typical supernova remnant might contain as much dust as 10,000 Earths. That's a lot of dust. All of it drifting through space. All of it part of the quiet supernova. Scientists used to think that most cosmic dust came from other sources, from dying stars that didn't explode. But recent studies have changed that. Astronomers now think that supernovas might be one of the main sources of dust in the universe. They found huge amounts of dust in young supernova remnants, more than they expected. This dust is important. It helps form new stars. It helps form planets. Without it, the universe would be very different. So supernovas don't just create elements. They also create the dust that helps build new worlds. It's all connected. The death of one star helps birth another. Using infrared telescopes, astronomers have discovered something surprising. Supernova remnants can create dust very quickly, in just a few years after the explosion. Scientists studying Cassiopeia A supernova remnant about 11,000 light-years away, found that it contains about 10,000 times the mass of Earth in dust. That's a lot of dust, all created in the explosion, all drifting through space, all part of the quiet supernova. But here's the interesting part. Not all supernovas create the same amount of dust. Some create more, some create less. Scientists are still trying to figure out why. It might depend on the type of star, or the conditions of the explosion, or the surrounding material. It's a mystery, but we're learning. Every new observation teaches us something. Every quiet supernova has its own story. its own amount of dust, its own contribution to the galaxy. The gas in the supernova remnant is mostly hydrogen and helium, but it also contains heavier elements: carbon, oxygen, nitrogen, iron, and more. These elements were created in the star. They were scattered by the explosion, and now they're part of the remnant. They're enriching the interstellar medium, making it richer in heavy elements. This enriched material will eventually become part of new stars, new planets, maybe even new life. The composition of a supernova remnant tells us about the star that created it. Different types of stars create different elements. A massive star creates a lot of oxygen. A white dwarf that explodes creates a lot of iron. By studying the composition of a remnant, we can learn about the star that died, what type it was, how massive it was, how it lived, and how it died. Supernova remnants also tell us about the explosion itself, how much energy was released, how fast the material was ejected, what direction it went. By studying remnants, we can learn about supernovas. Even supernovas that happened thousands of years ago, even supernovas we never saw explode. The remnant is a record, a fossil, a memory of the explosion. Some supernova remnants are very young, only a few hundred years old. These are still expanding rapidly. They're still very hot. They glow brightly in X-rays. They're easy to see, but they're also rare. Most remnants are older, thousands of years old. They've expanded. They've cooled. They're quieter, more peaceful. The quiet supernova, the beautiful aftermath. Older remnants are larger, but they're also dimmer. The material has spread out. The density has decreased. They're harder to see, but they're still there. Still expanding, still drifting through space. Still part of the galaxy. Still beautiful, still quiet. The age of a supernova remnant can be estimated in several ways. By measuring how fast it's expanding, by studying its composition, by looking at historical records. If we know when the supernova was seen, we know how old the remnant is. The Crab Nebula is about 970 years old. We know because Chinese astronomers recorded the supernova in 1054. The Veil Nebula is about 8,000 years old. We know from studying its expansion. Some remnants are very old, tens of thousands of years old. These are large, very large, hundreds of light years across, but they're also very thin, very dim. Hard to see, but they're still there, still expanding, still part of the galaxy, still beautiful in their own way. The quietest supernovas, the most peaceful remnants. Supernova remnants don't exist in isolation. They interact with the surrounding material, the interstellar medium, other remnants, even other stars. These interactions can create beautiful structures, bubbles, shells, filaments. They can trigger star formation. They can enrich the galaxy with heavy elements. They're part of the larger ecosystem of the galaxy. The galaxy is full of supernova remnants. Some are young, some are old, some are large, some are small. But they're all there, all expanding, all drifting, all beautiful, all quiet. They're the peaceful aftermath of violent explosions, the quiet supernovas, the beautiful clouds that drift through space. If you could travel through the galaxy, you would pass through many supernova remnants. Some would be visible, glowing with beautiful colors. Others would be invisible, too thin to see, but they're all there, all part of the galaxy, all part of the cycle of star birth and death, all beautiful, all quiet. Chapter 3, Supernova Remnants, the quiet phase. After a supernova explodes, the light fades, the brightness dims, but something remains, a supernova remnant, a cloud of gas and dust, expanding slowly through space. This is the quiet phase, the peaceful aftermath, the beautiful cloud that drifts through the galaxy for thousands of years. A supernova remnant starts as a shell of material, ejected by the explosion, traveling outward at thousands of kilometers per second. But as it expands, it slows down. It interacts with the surrounding material. It creates a shockwave. The shockwave compresses the material. It heats it. It makes it glow. This is when the remnant is brightest, when it's easiest to see. But over time, the expansion slows. The material cools. The brightness fades. But the remnant remains. It continues to expand. It continues to drift. It becomes quieter, more peaceful. The quiet supernova. The beautiful cloud that floats through space. The structure of a supernova remnant changes over time. When it's young, it's a simple shell, a bubble of material. But as it ages, it becomes more complex. It develops filaments, long, thin structures. It develops knots, dense regions. It develops bubbles, regions of different density. The structure becomes intricate, beautiful, like a cosmic cloud. The filaments in a supernova remnant are where the material is compressed, where the shockwave has passed. They're dense. They glow brightly. They're beautiful, delicate, like threads of light. They show us the structure of the remnant, how it's expanding, how it's interacting with the surrounding material. The filaments can be very long, hundreds of light years long, but they're also very thin, only a few light years thick. They're like cosmic threads, woven through space, beautiful, delicate, peaceful, part of the quiet supernova. The knots in a supernova remnant are dense regions, places where the material has clumped together. They're brighter than the surrounding material. They glow more intensely. They're like beads on a string, or like stars in a cloud. They're beautiful. They add texture to the remnant. They make it more interesting, more complex. The bubbles in a supernova remnant are regions of different density. Some are denser, some are less dense. They create patterns, beautiful patterns, like clouds in the sky. But these are cosmic clouds, clouds of gas and dust, drifting through space, peaceful, quiet, beautiful. The colors in a supernova remnant come from different elements. Hydrogen glows red, oxygen glows green and blue, sulfur glows red, nitrogen glows red. These colors tell us what the remnant is made of. They tell us the story of the star that died. They're beautiful. They make the remnant look like a cosmic painting, a work of art, created by nature, by the death of a star. The Veil Nebula is a perfect example of a quiet supernova remnant. It's about 8,000 years old. It's expanded to about 110 light years across. It glows with beautiful colors, red, green, blue. It has filaments, long, thin structures. It looks like a veil, a delicate veil floating in space. It's peaceful. It's quiet. It's beautiful. The quiet supernova. The Crab Nebula is younger, only about 970 years old. It's smaller, about 11 light years across, but it's still expanding, still glowing, still beautiful. It has a pulsar at its center, a spinning neutron star, the remains of the star's core. It pulses 30 times per second, a steady rhythm, a cosmic heartbeat. The pulsar adds energy to the remnant. It keeps it glowing. It makes it brighter than it would be otherwise. The Vela supernova remnant is another beautiful example. It's about 11,000 years old. It's large, about 100 light years across. It's in the constellation Vela, the sails. It glows with beautiful colors. It has filaments. It has bubbles. It's complex. It's beautiful. It's peaceful. The quiet supernova. What makes the Vela remnant special is that it has a pulsar at its center, just like the Crab Nebula. But this pulsar is different. It's moving, fast, about 1/100 kilometers per second. That's fast, very fast. The explosion must have given it a kick, a powerful kick, that sent it flying through space. The pulsar is now offset from the center of the remnant. It's not where you'd expect it to be. It's been traveling for 11,000 years, moving away from where the explosion happened, still pulsing, still spinning, but in a different place. It's a reminder that supernova explosions aren't always symmetric. Sometimes they give things a push, a kick, that sends them flying. The quiet supernova, but with a moving heart. Scientists have also discovered that the Vela remnant is actually interacting with another remnant nearby, the Puppis A remnant. They're both expanding, they're both pushing into the same space. They're creating beautiful structures, complex patterns. It's like two clouds meeting, two quiet supernovas, interacting, creating something new, something beautiful, the peaceful aftermath of two cosmic explosions. Supernova remnants are not static, they're dynamic, they're changing, they're expanding, they're cooling, they're mixing with the surrounding material, they're evolving. But from our perspective, the changes are slow, very slow. Over a human lifetime, a remnant might expand by a few light years. But that's still huge. It's still expanding, still changing, still beautiful. The expansion of a supernova remnant is driven by the energy from the explosion. The material was ejected with a lot of energy, kinetic energy, the energy of motion. This energy keeps the material moving, keeps it expanding. But over time, the expansion slows. The material loses energy. It interacts with the surrounding material. It creates drag. The expansion slows down, but it doesn't stop. It continues. For thousands of years, the temperature in a supernova remnant decreases over time. When it's young, it's very hot, millions of degrees. But as it expands, it cools. The material spreads out. The density decreases. The temperature drops. After 10,000 years, a typical remnant might be only a few thousand degrees, still hot, but much cooler than when it was young. The cooling happens in several ways. The material expands. Expansion causes cooling. The material radiates energy. It emits light. X-rays, other radiation. This radiation carries away energy. The material cools. The material also mixes with cooler material. The interstellar medium. This mixing also causes cooling. As the remnant cools, the types of radiation it emits change. When it's hot, it emits X-rays, high energy radiation. But as it cools, it emits less X-rays, more visible light, more radio waves. The spectrum shifts. The colors change. The remnant evolves. It becomes quieter, more peaceful. The density in a supernova remnant also decreases over time. When it's young, the material is dense, relatively dense. But as it expands, it spreads out. The density decreases. After 10,000 years, a typical remnant might have a density of only a few atoms per cubic centimeter. That's very thin, much thinner than the Earth's atmosphere. But it's not empty. There's still material there, still gas, still dust, still beautiful. The magnetic fields in a supernova remnant are complex. They're created by the explosion. They're amplified by the shock wave. They're twisted by the expansion. They create structure. They influence how the material moves. They affect the radiation. They're important, but they're also invisible. We can't see them directly, but we can see their effects. Magnetic fields can create filaments. They can align dust grains. They can affect the radiation. They're part of the remnant, part of its structure, part of its beauty, part of the quiet supernova. Supernova remnants also contain cosmic rays, high-energy particles, protons, electrons, other particles. These particles are accelerated by the shock wave. They gain energy. They become cosmic rays. They travel through space. They can reach Earth. They're part of the cosmic radiation that constantly bombards our planet. Scientists have been studying cosmic rays for over 100 years, but they're still not sure exactly where they all come from. Supernova remnants are one source, but probably not the only one. Some cosmic rays might come from other sources, black holes, active galaxies, even the Sun. But supernova remnants are likely a major source. The shock waves in these remnants are perfect particle accelerators. They can speed up particles to incredible energies, much higher than anything we can create on Earth. These particles then travel through space. Some reach Earth. They hit our atmosphere. They create showers of particles. Scientists detect these showers. They study them. They try to figure out where they came from. It's like cosmic detective work, tracing particles back to their sources, back to the quiet supernovas, back to the peaceful remnants. Using the Fermi Gamma Ray Space Telescope, astronomers have found direct evidence that supernova remnants accelerate cosmic rays. They've detected gamma rays coming from these remnants. Gamma rays are created when cosmic rays interact with gas. So if we see gamma rays from a remnant, we know cosmic rays are being created there. Scientists have found this in several remnants, including the Crab Nebula and Tycho's supernova remnant, and others. It's proof. Supernova remnants are cosmic particle accelerators. The quiet supernova is still at work, still creating, still accelerating particles to incredible speeds. But here's something interesting. Not all cosmic rays come from supernova remnants. Scientists estimate that maybe 20 to 30% come from these quiet supernovas. The rest come from other sources. Some from the Sun, some from black holes, some from active galaxies. Some we don't know where they come from. It's still a mystery, but we're learning. Every new discovery helps. Every quiet supernova teaches us something about cosmic rays, about particle acceleration, about the universe. Cosmic rays from supernova remnants are important. They're a source of high-energy particles. They help us understand the universe. They're part of the remnant, part of its legacy, part of the quiet supernova. The interaction between a supernova remnant and the surrounding material is complex. The remnant pushes into the interstellar medium. It compresses it. It heats it. It creates a shock wave. This shock wave can trigger star formation. It can compress gas clouds. It can cause them to collapse, to form new stars. So supernova remnants don't just drift. They also create. They trigger star formation. They're part of the cycle of star birth and death. Stars are born. They live. They die. They explode. Their remnants trigger new star formation. The cycle continues. It's beautiful. It's peaceful. It's the quiet supernova. The lifetime of a supernova remnant depends on several factors. The energy of the explosion, the density of the surrounding material, the size of the remnant. Typically, a remnant is visible for about 100,000 years. After that, it's too thin, too dim. It has mixed with the surrounding material. It has become part of the interstellar medium. But the elements remain. The heavy elements. They're still there, still drifting, still waiting to become part of something new. Some remnants are older, much older, hundreds of thousands of years old. These are very large, very thin, very dim, hard to see, but they're still there, still expanding, still part of the galaxy, still beautiful in their own way. The quietest supernovas, the most peaceful remnants. Supernova remnants are beautiful. They're peaceful. They're quiet. They're the aftermath of violent explosions. but they're also beautiful clouds, drifting through space, glowing with soft colors, expanding slowly, cooling gradually, mixing with the galaxy, becoming part of something larger, the quiet supernova, the peaceful cloud, the beautiful remnant. Chapter 4. What would it be like inside? A journey through the quiet supernova. Imagine floating inside a supernova remnant. What would you see? What would you feel? What would it be like? Let's take a journey through the quiet supernova, a journey through the peaceful cloud that remains after a star's death. First, you would see the gas, glowing gas, red from hydrogen, green and blue from oxygen, other colors from other elements. The colors would be soft, gentle, not bright like a star, but soft like a cloud, a cosmic cloud, beautiful, peaceful, quiet. The gas would be very thin, much thinner than Earth's atmosphere, so thin that you could see through it. You could see the stars beyond, the galaxy beyond. You'd be floating in a cloud, but you could still see the universe around you. The cloud would be like a veil, a thin veil, a beautiful veil, but a veil you could see through. The gas would be moving, slowly, very slowly, expanding outward, drifting, floating, like a cloud in the sky. But this is a cosmic cloud, a cloud of gas and dust, a cloud that's been drifting through space for thousands of years, a cloud that will continue to drift for thousands more. You would see filaments, long, thin structures, glowing brightly, like threads of light, woven through space, beautiful, delicate, peaceful. They would stretch for light years, but they would be thin, only a few light years thick. They would be like cosmic threads, beautiful threads, peaceful threads, part of the quiet supernova. You would see knots, dense regions, brighter than the surrounding material, like beads on a string, or like stars in a cloud. They would glow more intensely. They would add texture. They would make the cloud more interesting, more complex, more beautiful. You would see bubbles, regions of different density, some denser, some less dense. They would create patterns, beautiful patterns, like clouds in the sky. But these are cosmic clouds, clouds of gas and dust, drifting through space, peaceful, quiet, beautiful. The colors would change as you moved. Different regions would have different compositions, different elements, different colors. You would float through red regions, hydrogen-rich regions. You would float through green and blue regions, oxygen-rich regions. You would float through other colors, other elements. The colors would shift. They would change. They would be beautiful. They would be peaceful. The temperature would vary. Near the center, where the explosion happened, it would be hot, millions of degrees, but you wouldn't feel it. The material is so thin that there aren't enough particles to transfer heat effectively. You would be surrounded by hot gas, but you wouldn't feel hot. The heat would be there, but it wouldn't affect you, not directly. Scientists have actually measured temperatures in supernova remnants. They use X-ray telescopes. These can see the hot gas. The hottest parts can reach 10 million degrees. That's hotter than the center of the sun. But the material is so thin, only a few atoms per cubic centimeter. On Earth, the air has billions of atoms per cubic centimeter. So even though the gas is hot, there's so little of it that you wouldn't feel the heat. It's like being near a tiny, super hot flame. The flame is hot, but it's so small that you barely feel it. That's what it would be like in a supernova remnant. Hot gas, but so thin that it feels like nothing. Using the Chandra X-ray Observatory, astronomers have mapped temperatures across many supernova remnants. They found that temperatures vary a lot, from millions of degrees near the center to thousands of degrees at the edges. The hottest regions are where the shock wave is strongest, where material is being compressed, where energy is being released. These regions glow brightly in X-rays. They're easy to see, but they're also small. Most of the remnant is cooler, quieter, more peaceful. The quiet supernova. Interestingly, scientists have also discovered that some remnants have regions that are even hotter, up to 50 million degrees. These are rare, but they exist. They're usually near pulsars, or in regions where the shock wave is interacting with dense material. These super hot regions are fascinating. They show us that even in the quiet phase, there's still energy, still activity, still beauty. The quiet supernova, but with hotspots, with the regions of intense activity, even in the peaceful cloud. As you moved outward, the temperature would decrease. It would get cooler, but still hot by human standards, thousands of degrees. But again, you wouldn't feel it. The material is too thin, too sparse. The heat is there, but it's not transferred to you. You would float through it, peacefully, quietly. The pressure would be very low, almost zero, much lower than Earth's atmosphere, much lower than the best vacuum we can create on Earth. You would need a spacesuit to breathe, to maintain pressure. But the material itself wouldn't press on you. It's too thin, too sparse. You would float through it, like floating through air, but thinner, much thinner. You would see dust, tiny grains of carbon and silicon. They would be floating, drifting, like snowflakes, but smaller, much smaller, about 0.1 micrometers across, 1,000 times smaller than a grain of sand. But there would be many of them, millions, billions, trillions. They would be like cosmic snow, beautiful, peaceful, quiet. The dust would scatter light. It would make the cloud glow. It would add to the colors. It would make the cloud more beautiful, more interesting, more complex. The dust is part of the remnant, part of the quiet supernova, part of the beautiful cloud. You would hear nothing. Space is silent. There's no air to carry sound, no medium for sound waves. You would float in silence, complete silence. The cloud would be quiet, peaceful, silent, beautiful. The quiet supernova, the silent cloud, the peaceful remnant. But you would see radiation, visible light, the colors, but also invisible light, ultraviolet, X-rays, radio waves. You wouldn't see these directly, but they would be there, part of the remnant, part of the quiet supernova, part of the beautiful cloud. If you had special sensors, you could detect the X-rays, the hot gas emitting high-energy radiation. You could detect the radio waves, the structure of the remnant, the magnetic fields. You could see more than your eyes could see. You could understand more. But even with just your eyes, you would see beauty. You would see a cosmic cloud, a beautiful cloud, a peaceful cloud, the quiet supernova. You would feel weightless. There's no gravity to speak of. The remnant is so large and the material is so thin that gravity is negligible. You would float, drift, move slowly, peacefully, quietly. You would be like a feather, floating in a cosmic breeze. Beautiful, peaceful, quiet. You would see the stars beyond, through the cloud. The cloud would be like a veil, a thin veil, a beautiful veil, but a veil you could see through. You would see the galaxy, the Milky Way, beautiful, peaceful, quiet. You would see other stars, other remnants, other clouds, the universe around you, beautiful, peaceful, quiet. You would see the structure of the remnant, the filaments, the knots, the bubbles, the patterns. They would be beautiful, complex, intricate, like a cosmic painting, a work of art, created by nature, by the death of a star. Beautiful, peaceful, quiet. You would see the expansion, the material moving outward, slowly, very slowly, but moving, drifting, floating. The remnant is still expanding, still growing, still changing, but slowly, very slowly. From your perspective, it would seem still, peaceful, quiet, beautiful. You would see the colors shift as you moved, as the composition changed. Different regions, different elements, different colors. The colors would be soft, gentle, not bright, but soft, like a cloud, a cosmic cloud, beautiful, peaceful, quiet. You would feel small. The remnant is huge, tens or hundreds of light years across. You would be tiny, insignificant, but also part of something larger, part of the remnant, part of the galaxy, part of the universe. You would be floating in a cosmic cloud, a beautiful cloud, a peaceful cloud, the quiet supernova. You would feel peaceful. The remnant is quiet, peaceful, beautiful. There's no violence here, no explosion, no destruction, just a cloud, a beautiful cloud, drifting through space, peaceful, quiet, beautiful, the quiet supernova. You would feel connected to the star that died, to the explosion that happened, to the elements that were created. You are made of star stuff, the same elements, the same atoms. You are connected to the star, to the explosion, to the remnant, to the quiet supernova. You would feel wonder, awe, the beauty, the peace, the quiet. The remnant is beautiful. It's peaceful. It's quiet. It's amazing. You would feel wonder, awe, gratitude for being able to see it, to experience it, to be part of it, the quiet supernova. You would want to stay, to float, to drift, to be part of the cloud, part of the remnant, part of the quiet supernova. But you would have to leave, eventually, to return to Earth, to tell others, to share the experience, the beauty, the peace, the quiet supernova. But the memory would remain, the image, the feeling, the wonder, the awe, the beauty, the peace, the quiet supernova, the beautiful cloud, the peaceful remnant. The memory would remain forever. A memory of floating in a cosmic cloud, a memory of the quiet supernova. Chapter 5. The Science of Supernovas. Understanding the explosions. To understand supernova remnants, we need to understand supernovas, the explosions that create them, the science behind these cosmic events, the processes that turn a dying star into a beautiful cloud. A star shines by fusing hydrogen into helium. This process releases energy. It's what makes stars hot and bright, but eventually the hydrogen runs out. The star starts fusing heavier elements. Helium becomes carbon. Carbon becomes oxygen. Oxygen becomes silicon. And silicon becomes iron. But iron is special. Iron can't be fused to release energy. When a star's core becomes iron, fusion stops. Without fusion, the star's core collapses. It shrinks from the size of Earth to the size of a city. The temperature rises to billions of degrees. The pressure increases to incredible levels. The core becomes incredibly dense. A teaspoon of it would weigh billions of tons on Earth. Then, the outer layers of the star fall inward. They hit the collapsed core, and they bounce back. This creates a shock wave, a wave of energy, traveling outward at incredible speed. This is the supernova explosion. The explosion ejects material, the outer layers of the star, traveling outward at thousands of kilometers per second. The material expands. It forms a shell, a bubble. This is the beginning of the supernova remnant. The material ejected by a supernova contains different elements: hydrogen, helium, carbon, oxygen, nitrogen, silicon, iron, and heavier elements: gold, silver, platinum, uranium, all created in the star or in the explosion itself. The composition depends on the type of star. A massive star creates a lot of oxygen. A white dwarf that explodes creates a lot of iron. By studying the composition of a remnant, we can learn about the star that created it. Scientists have found something surprising though. Not all supernovas create the same elements. Some create more of certain elements than others. A star's mass matters. Its age matters. Even its location in the galaxy matters. Astronomers have discovered that stars in different parts of the galaxy have different compositions. Stars in the center of the galaxy are richer in heavy elements. Stars in the outer parts are poorer. This tells us about the galaxy's history, where supernovas have happened, where new stars have formed. It's like cosmic archaeology. By studying the elements in supernova remnants, we can learn about the galaxy's past. We can trace where elements came from. We can understand how the galaxy evolved. It's all written in the elements, in the quiet supernova remnants, waiting to be read. The energy released by a supernova is enormous, about 10 to the 44th power joules. That's a 1 followed by 44 zeros. An incredible amount of energy. Most of it is in the form of neutrinos, ghostly particles that barely interact with matter. But some is in the form of light, visible light, ultraviolet, X-rays, gamma rays. To understand just how much energy this is, imagine this. If you could capture all the energy from a single supernova, you could power the entire Earth for billions of years. That's how much energy we're talking about. But we can't capture it. It's released in all directions, into space. Most of it is lost, forever. But some of it reaches us, as light, as neutrinos, as cosmic rays. We feel its effects, even from far away, even from thousands of light years away. The quiet supernova, still powerful, still affecting the galaxy, even in its peaceful phase. Scientists have also discovered that the energy isn't released evenly. Some parts of the explosion are more energetic than others. The material moving fastest carries the most energy. The material moving slowest carries less. This creates the structure we see in remnants. The filaments, the knots, the bubbles, they're all shaped by energy, by how it was released, by how it's still being released. The quiet supernova, still energetic, still powerful, but peaceful, beautiful. To put this in perspective, scientists have calculated that a single supernova releases more energy in 1 second than our sun will release in its entire 10 billion year lifetime. That's how powerful these explosions are. But here's the interesting part. Even though supernovas are incredibly bright, most of their energy is invisible. It's in those neutrinos, billions of them, streaming out in all directions. We only detected neutrinos from one supernova, SN 1987A. In 1987, scientists detected 24 neutrinos, just 24, from an explosion that released billions and billions of them. But those 24 were enough. They proved that our understanding of supernovas was correct. The neutrinos arrive first, before the light. They pass through everything, even the star itself. They're the first messengers of a star's death. The light from a supernova can be seen from billions of light years away. The brightness peaks after about 20 days. During this time, a supernova can outshine an entire galaxy. Then it starts to fade, over weeks or months, until it's gone. But the remnant remains. The material ejected by a supernova travels at different speeds. The fastest material moves at about 10,000 kilometers per second. That's about 3% of the speed of light. Very fast. But most material moves slower, about 1,000 to 5,000 kilometers per second. Still fast, but not as fast. As the material expands, it slows down. It interacts with the surrounding material, the interstellar medium. It creates a shock wave. The shock wave compresses the material. It heats it. It makes it glow. This is when the remnant is brightest. Over time, the expansion slows, the material cools, the brightness fades, but the remnant remains. It continues to expand. It continues to drift. It becomes quieter, more peaceful. The quiet supernova. The structure of a supernova remnant changes over time. When it's young, it's a simple shell, a bubble of material. But as it ages, it becomes more complex. It develops filaments, knots, bubbles. The structure becomes intricate, beautiful. The filaments are where the material is compressed, where the shock wave has passed. They're dense. They glow brightly. They're beautiful, delicate, like threads of light. The knots are dense regions, places where the material has clumped together. They're brighter than the surrounding material. They glow more intensely. They add texture. They make the remnant more interesting. The bubbles are regions of different density, some denser, some less dense. They create patterns, beautiful patterns, like clouds in the sky. But these are cosmic clouds. The colors come from different elements. Hydrogen glows red. Oxygen glows green and blue. Sulfur glows red. Nitrogen glows red. These colors tell us what the remnant is made of. They tell us the story of the star that died. The temperature in a supernova remnant decreases over time. When it's young, it's very hot, millions of degrees, but as it expands, it cools. After 10,000 years, a typical remnant might be only a few thousand degrees, still hot, but much cooler than when it was young. The density also decreases over time. When it's young, the material is dense, relatively dense, but as it expands, it spreads out. The density decreases. After 10,000 years, a typical remnant might have a density of only a few atoms per cubic centimeter. That's very thin, much thinner than the Earth's atmosphere. The magnetic fields in a supernova remnant are complex. They're created by the explosion. They're amplified by the shock wave. They're twisted by the expansion. They create structure. They influence how the material moves. They affect the radiation. Supernova remnants also contain cosmic rays, high-energy particles, protons, electrons, other particles. These particles are accelerated by the shock wave. They gain energy. They become cosmic rays. They travel through space. They can reach Earth. The interaction between a supernova remnant and the surrounding material is complex. The remnant pushes into the interstellar medium. It compresses it. It heats it. It creates a shock wave. This shock wave can trigger star formation. It can compress gas clouds. It can cause them to collapse, to form new stars. So supernova remnants don't just drift. They also create. They trigger star formation. They're part of the cycle of star birth and death. Stars are born. They live. They die. They explode. Their remnants trigger new star formation. The cycle continues. The lifetime of a supernova remnant depends on several factors: the energy of the explosion, the density of the surrounding material, the size of the remnant. Typically, a remnant is visible for about 100,000 years. After that, it's too thin, too dim. It has mixed with the surrounding material. It has become part of the interstellar medium. But the elements remain, the heavy elements. They're still there, still drifting, still waiting to become part of something new. Supernova remnants are important for the galaxy. They enrich the interstellar medium with heavy elements. They create shock waves that compress gas clouds. These compressed clouds can collapse and form new stars. So supernovas don't just destroy, they also create. They're part of the cycle of star birth and death. The study of supernova remnants helps us understand supernovas, even supernovas that happened thousands of years ago, even supernovas we never saw explode. The remnant is a record, a fossil, a memory of the explosion. By studying remnants, we can learn about the explosion, how much energy was released, how fast the material was ejected, what direction it went. We can learn about the star, what type it was, how massive it was, how it lived, and how it died. We can also learn about the universe, the composition of the interstellar medium, the processes of star formation, the cycle of stellar evolution. Supernova remnants are windows into the past, into the processes that shape the galaxy, into the universe itself. The science of supernovas is complex, but it's also beautiful. The explosions are violent, but the remnants are peaceful. They're quiet, they're beautiful, they're the quiet supernova, the peaceful cloud, the beautiful remnant. Chapter 6. Latest discoveries and mysteries. What we're still learning. Scientists are still learning about supernovas and their remnants. Every year, new discoveries are made. New mysteries are uncovered. New questions are asked. The study of supernovas is ongoing. It's exciting. It's fascinating. It's full of wonder. Recent discoveries have revealed new types of supernovas. Some are very bright, brighter than normal. Some are very dim, dimmer than normal. Some explode in unusual ways. They don't follow the patterns we expect. They're mysterious. They're fascinating. Some supernovas are surrounded by dense shells of material, gas and dust, ejected by the star before it exploded. When the supernova explodes, it hits this shell. The interaction creates a bright flash, a rapid brightening, then a rapid fading. These are called type twin supernovas. They're rare, but they're beautiful. Some supernovas are very dim, much dimmer than expected. They're called subluminous supernovas, or failed supernovas. They might be stars that tried to explode, but didn't have enough energy. They collapsed into black holes without the bright explosion. These are mysterious. We're still learning about them. Scientists have found that these dim supernovas might be more common than we thought. They're just harder to see because they're dim. They don't outshine galaxies. They don't light up the sky. They're quiet, very quiet, almost silent, but they still happen. Stars still die. They just do it more quietly, more subtly. It's a reminder that not all stellar deaths are dramatic. Some are quiet from the start. The quietest supernovas, the most mysterious deaths. Interestingly, some astronomers think that most massive stars might die this way, quietly, without a bright explosion, just collapsing into black holes. If that's true, then we're missing most supernovas. We're only seeing the bright ones, the dramatic ones. The quiet ones are hidden, invisible, but they're still there, still happening, still creating black holes, still part of the cosmic cycle. The quietest supernovas, the most mysterious. Scientists have a theory about these failed supernovas. They think some massive stars might collapse directly into black holes. Without the bright explosion, the outer layers might just fall in, disappearing into the black hole. No light, no remnant, just darkness. But we're not sure. Because if this happens, we wouldn't see it. That's the problem. How do you study something you can't see? Astronomers are looking for clues, stars that just disappear without explanation. They found a few candidates, stars that were there, then gone. No supernova, no remnant, just gone. These might be failed supernovas, stars that collapsed into black holes, quietly, in the dark. It's a reminder that not all star deaths are dramatic. Some stars might just fade away, into nothingness, into a black hole. Some supernovas leave behind unusual remnants. Some have strange shapes. Some have unusual compositions. Some have unexpected structures. They don't fit the patterns we know. They're unique. They're fascinating. They're beautiful. Recent observations have revealed new details about supernova remnants. The structure is more complex than we thought. There are more filaments, more knots, more bubbles. The patterns are intricate, beautiful, fascinating. The composition is also more complex. There are more elements, in different ratios. The composition varies from place to place. It's not uniform. It's patchy, complex, beautiful. The expansion is also more complex. Different parts expand at different rates. The shape changes over time. It's not a simple sphere. It's irregular, twisted, distorted, beautiful. Recent discoveries have also revealed new processes, new ways that remnants interact with their surroundings, new ways they trigger star formation, new ways they enrich the galaxy. The processes are complex. They're fascinating. They're beautiful. Some remnants have pulsars at their centers, spinning neutron stars, the remains of the star's core. They emit beams of radiation, like cosmic lighthouses. The beams sweep across space. When they point toward Earth, we see pulses, flashes of light or radio waves. Recent observations have revealed new details about pulsars. Some spin very fast, hundreds of times per second. Some spin slowly, once every few seconds. Some have companions, binary pulsars. They orbit each other. They're fascinating. Some pulsars are in unusual locations, not at the center of the remnant, but offset, or outside the remnant entirely. They were kicked away by the explosion. They're traveling through space, alone, but still pulsing, still beautiful. Recent discoveries have also revealed new ways to study supernovas, new telescopes, new instruments, new techniques. We can see more. We can understand more. We can learn more. Space telescopes can see in wavelengths that are blocked by Earth's atmosphere. X-rays, ultraviolet, infrared. They reveal details we couldn't see before. They show us the hot gas, the structure, the composition. They're amazing. Ground-based telescopes are also getting better. Larger mirrors, better instruments, better techniques. They can see fainter objects. They can see more detail. They can see faster changes. They're amazing. Computer simulations are also getting better. More powerful computers, better models, more accurate physics. They can simulate the explosion, the expansion, the evolution. They can help us understand what we observe. They're amazing, but there are still mysteries, many mysteries. Questions we can't answer yet. Questions that drive scientists to keep studying, keep exploring, keep learning. Why do some supernovas explode in unusual ways? Why are some so bright? Why are some so dim? Why do some leave behind unusual remnants? We don't know, not yet, but we're learning. How do supernova remnants trigger star formation? What are the exact processes? How efficient are they? We're learning, but there's still more to discover. What happens to supernova remnants after 100,000 years? Do they completely disappear, or do they leave behind traces? We're learning, but there's still more to discover. How do magnetic fields affect supernova remnants? How do they shape the structure? How do they influence the evolution? We're learning, but there's still more to discover. How do cosmic rays form in supernova remnants? What are the exact processes? How efficient are they? We're learning, but there's still more to discover. These mysteries drive scientists. They inspire curiosity. They lead to new discoveries. They make the study of supernovas exciting, fascinating, full of wonder. Recent discoveries have also revealed connections between supernovas and other cosmic events. Gamma-ray bursts, gravitational waves, neutrino bursts. These connections are fascinating. They help us understand the universe better. Some supernovas are associated with gamma ray bursts, short, intense flashes of gamma rays, the most energetic events in the universe. They might be caused by the collapse of massive stars, the same process that creates supernovas. They're fascinating. Some supernovas might be associated with gravitational waves, ripples in space-time, caused by the collapse of massive objects. We've detected gravitational waves from black hole mergers, but not yet from supernovas. But we might. Soon. It's exciting. Some supernovas are associated with neutrino bursts, floods of ghostly particles, emitted during the collapse. We've detected neutrinos from one supernova, SN 1987A, in the Large Magellanic Cloud. It was amazing. We might detect more. In the future, it's exciting. SN 1987A was special. It was the closest supernova we've seen in over 400 years, only 168,000 light years away. Close enough to study in detail. Scientists detected its neutrinos on February 23, 1987. 3 hours before the light arrived, the neutrinos traveled through space, through the star, through everything, and reached Earth first. This proved that neutrinos really do come from supernovas. It confirmed what scientists had predicted for decades. But there was a surprise. The neutrinos arrived over a period of 13 seconds, not all at once. This told scientists something new. The collapse doesn't happen instantly. It takes time. Even though it seems fast to us, the star's core collapses over several seconds. It's a process, not a single moment. Scientists are still learning from those 24 neutrinos. They're still teaching us about how stars die. But SN 1987A had more surprises. The star that exploded was a blue supergiant. Scientists expected it to be a red supergiant. That's what most massive stars become before they explode. But this one was blue, hotter, different. Scientists are still trying to understand why. It might have been in a binary system. It might have lost mass before exploding. It might have been different from the start. We're not sure. But it's teaching us that stars don't always follow the rules. They're complex. They're individual. Each one is unique. Even in death, even in explosion, even in the quiet supernova that follows. Today, SN 1987A has a beautiful remnant. It's still young, only about 37 years old, but it's expanding, still glowing, still beautiful. Astronomers have watched it grow. They've seen rings of material light up. They've seen the shockwave hit gas that the star ejected before it exploded. It's like watching a movie, in slow motion, over decades. The quiet supernova, growing, expanding, becoming more beautiful, more peaceful. With each passing year, these connections help us understand supernovas better. They help us understand the universe better. They're fascinating, they're beautiful. They're part of the quiet supernova, part of the peaceful cloud, part of the beautiful remnant. The study of supernovas is ongoing. It's exciting, it's fascinating, it's full of wonder. New discoveries are made every year. New mysteries are uncovered. New questions are asked. The journey continues. The exploration continues. The wonder continues. Supernova remnants are beautiful. They're peaceful. They're quiet. They're the aftermath of violent explosions. But they're also beautiful clouds, drifting through space, glowing with soft colors, expanding slowly, cooling gradually, mixing with the galaxy, becoming part of something larger. They're the quiet supernova, the peaceful cloud, the beautiful remnant. They're amazing, they're fascinating, they're full of wonder. And we're still learning about them, still discovering, still exploring. The journey continues, the wonder continues, the quiet supernova continues. And now the stars begin to dim behind your thoughts. We've drifted through 100 quiet truths, from the violent explosions that create supernovas to the peaceful remnants that drift through space, from the elements that were forged in dying stars to the clouds that will become new stars, from the bright flashes that light up the sky to the quiet clouds that glow softly in the dark. You've wandered through cosmic explosions. You've floated through peaceful clouds. You've learned about the death of stars and the birth of elements. You've discovered the quiet supernova, the beautiful remnant, the peaceful cloud that drifts through space. You are a part of this universe, not just a passenger on Earth, but a participant in its long and luminous unfolding. The iron in your blood was forged in supernovas. The oxygen you breathe was created in dying stars. The atoms of your body trace their lineage to cosmic explosions, to the quiet supernovas, to the peaceful remnants, to the beautiful clouds. Tonight, as you rest, supernovas are exploding somewhere far away. Their light is traveling through space. Their remnants are expanding. Their clouds are drifting. The cycle continues. Stars are born. They live. They die. They explode. Their remnants drift. They trigger new star formation. The cycle continues. Beautiful, peaceful, quiet. You are floating within it, a small warmth in the dark, resting in the spiral arm of a quiet, radiant sea, surrounded by the remains of stars that died long ago, connected to the explosions that created the elements you're made of, part of the quiet supernova, part of the peaceful cloud, part of the beautiful remnant. If you happen to still be awake, you can go ahead and watch the next video. But if you're drifting off, that's perfect too. The quiet supernova will still be there, still drifting, still beautiful, still peaceful, still quiet. Sweet dreams, and keep looking up at the stars. Remember, every time you see a supernova remnant, you're seeing the peaceful aftermath of a cosmic explosion. The quiet supernova, the beautiful cloud, the peaceful remnant. That's pretty special. Good night.